A pool is being drained and the water in the pool is changing at a rate of 50 liters per minute. What is the accumulated change in the amount of water in the pool between 0 and 10 minutes? Well, 10 minus 0 is 10. And it appears to me that you're losing 50 per 10, so negative 50 times 10, negative 500. 500 liters drained from the pool. Well, thank you so much for watching. I hope you enjoyed this video. May you all have a blessed day. Like and subscribe. A car's velocity in miles per hour is given by the function v of t equals 60 minus 10t, where t is the time in hours. What does the area between the graph of v of t and the t-axis from t equals 0 to t equals 3 represent? Well, if you take like the derivative of something, okay, so like say you have the velocity and you take the derivative of the velocity, you get acceleration. You work your way down. Well, working your way up is finding the area between the curve of a graph. So working your way up from the velocity gives you the position function, or in this case, displacement. So this is going to be displacement. The area under the curve is kind of like the opposite derivative, the antiderivative. And in this case, when you take the antiderivative of velocity, you end up with position function. Sometimes position function is given to you as s of t, so there's both. Either way, as the kids say, it's all good. Given the graph of f of x shown below, find the area under the curve between x equals 0 and x equals 6. All right, so we've got this picture going on right here, and we're going to use the idea of the additive property to find out what our three shapes are. So if I have a shape right here, okay, from 0 to 2, what I have appears to be a square with a height of 2, length of 2, everything is 2. Yippee. If I go from 2 to 4, it looks like what I have is I have a trapezoid. And what I'll do is I'll tilt it to the side so it looks like this. See what I'm doing? See what I'm doing? Where that part represents that part. And this part is going to be from 2 to 4. So your 2, the height of it is going to be 2. And I guess it would be the base. If we were looking at this, like we would call you 2, like that 2, we would call you 4. So that's 4. And your 2 as well. Don't care about you. One more shape though. And that shape would be a triangle. A triangle with a length of 2, height of 4. So let's get a different color. Triangle. Okay, height of 4, length of 2. Perfectly drawn. All right, so a square, easy peasy lemon squeezy. 2 times 2 is 4, length times width. Trapezoid's area is found by doing 1/2 of base sub 1 plus base sub 2 times the height of the whole thing. So in this case, that would be 1/2 of, you could be base sub 1, so 4. You could be base sub 2, so 2 times the height, which is 2. So 1/2 of 6 times 2 is going to be 6. So we'll go with that. The triangle, that area formula is 1/2 base times height. So 1/2 base would be 2 times height would be 4, which is going to end up being 4. So take all three of these numbers, all right, 4 plus 6 plus 4 is going to be 14. And that's going to be your area. Fun, 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 fun. A faulty shower spout continues to drip water after it's shut off. My goodness, the rate at which the water drips out can be modeled by the following graph here. Now, this is the rate. Okay, the time and the volume in, I guess that's milliliters per minute. How much water has dropped 6 minutes after the spout has been closed? Well, in order to do that, you are finding the area under the curve. And we care about 6 minutes. So I'm going to find the area of that quarter circle right there. And I'm going to find the area of what appears to be this triangle right here. Okay, so let's take a look at the quarter circle. Okay, let's take a look at the quarter circle. The quarter circle has a radius of 2. So that's really all that I need. So if I'm looking at like the area of a regular circle, the regular circle is pi r squared. Well, in this case, since it's a quarter circle, it's going to be 1/4 pi r squared. So since r is 2 in this case, you're looking at 1/4 pi times 2 squared. 2 squared is 4, so 1/4 of pi times 4, these guys cancel out. You're left with just pi. Now we have this triangle going on right here. This triangle appears to have a base. The base is going to be 4. The height is going to be 4. Okay, so a triangle, base of 4, height of 4. The area of a triangle is half of the base times the height. So half of the 4 times the 4, which is going to be 2 times 4, which is 8. So what we're looking at is if you add the black and if you add the red, if you add U and if you add U, you will get pi plus 8. So 11.14 something, blah, 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 blah. So we'll just say pi plus 8 to be more precise. Pi plus 8 milliliters. And that's going to be our guy. Yay. Everybody loves Riemann. Sums. Actually, not everybody loves Riemann sums. I personally hate them, but the idea behind it is you have an equation that when graphed is going to look a little something like this, right? And you are creating these like little boxes that's supposed to help you estimate, give or take, the volume underneath that curve. And nothing's ever perfect because if I were to use these little boxes, I mean, I'm overestimating here a little bit. But that's the idea of a Riemann sum. You are looking at rectangles and you're estimating the area under a curve, or in this case, a line, using those rectangles. In this case, we are doing right Riemann sums, which focuses mainly on the right side of something. So if we were looking at the integral between 0 and 6, and if this is supposed to demonstrate x plus 1, here's 0, here's 6. We're splitting this up into 3 equal subdivisions, so 3 equal things, and so I have to figure out what the right side of it is going to look like. Now, it's a little obvious, but if you don't have it obvious, we would call figuring out that difference the change of x. Now, the change of x is calculated by doing, this is b, this is a, this is your upper limit, that's your lower limit, so you do b minus a over the number of subdivisions that you are told to use. So in this case, you're going to do 6 minus 0 over 3. That's going to give you 6 over 3. It's going to give you 2, which means every one of these is going to be 2 units long, 2 units long, 2 units long. Now, since we're looking at the right side, we are focusing on the fact that u would be 2, u would be 4. We're going to focus on 2, 4, and 6. So those are going to be my endpoints, okay? What I do now is I evaluate this equation right here, which I'm going to call f of x. We evaluate at each of these 3 right endpoints at 2, 4, and 6. So I'm going to find f of 2, I'm going to find f of 4, and I'm going to find f of 6. What that does is that gives me the height at those spots according to my equation that I have written right here. So f of 2, and this is very friendly, f of 2 is going to be x plus 1, so 2 plus 1, which is 3. F of 4 is going to be 4 plus 1, which is 5. And f of 6 is going to be 6 plus 1, which is 7. Okay, so easy peasy. Now what I do next is I calculate the Riemann sums by multiplying the change of x to each f of x. So since u turned into 3, and u turned into 5, and u turned into 7, essentially what I need to do is I need to add up the area of all 3 of these. Since each of these have a length of 2, I'm going to multiply 2 to 3, 2 to 5, and 2 to 7. Okay, so 2 times 3 plus 2 times 5 plus 2 times 7 is going to be 6 plus 10 plus 14, which is going to add up to a nice perfect 30. So the area underneath this line is estimated to be around 30. Is it 30? No, because there's an overestimate here because these rectangles go a little bit above and beyond. But my estimate using 3 subdivisions is going to be 30. If you have more subdivisions, the estimate's greater, it's better, it's closer. Not greater, I shouldn't have said greater, it's going to be closer. But yeah, that's how you do a right Riemann sum to something that looks like this. To something that looks like this. Oh, like and subscribe. Use a left Riemann sum to approximate the integral between 1 and 5 of 3x squared minus 2. Now, let's take a look and understand what we're dealing with. 3x squared minus 2 when graphed is going to look something like this. Okay, definitely not perfect, but, you know, my heart was there. I care about stuff going on between 1 and 5, so 1 would probably be right around here, actually, right? And then let's scooch this up a little bit more so I can make it look a little bit better. We'll put 1 here, okay, and then we'll put 5 here. Not perfect, obviously not perfect. But what I'm going to do is, since I'm using a left Riemann sum to approximate it, is I'm going to make believe that I'm building 1, 2, 3, 4 rectangles, that when I add up these rectangles, I get an estimate of what this is going to look like. So essentially, I need to figure out how long each of these rectangles are and how tall each of these rectangles are. Well, in order to find out how long each of these rectangles are, I'm going to use the change of x formula, which is going to be b minus a. Now that's my upper limit, that's my lower limit. B minus a over some n being the number of 4 subdivisions I'm going to use. So b would be 5, a would be 1, n would be 4, 5 minus 1 is 4, 4 over 4 is 1. So each of these guys is going to be 1. Since I'm doing a left Riemann sum, I'm focusing on the left side of it. So I'm focusing on 1, and then 1 after that is going to be 2, 3, 4. So these green numbers that I'm going to use, 1, 2, 3, and 4, are going to be my left endpoints, and those are going to be the ones that I have to use. Now, I'm essentially finding areas of these rectangles based off of this information. I know the lengths of them. They're each 1 unit long. They each start at 1, 2, 3, and 4. How high are they? Well, I have to figure out what f of 1 is, what f of 2 is, what f of 3 is, and what f of 4 is. There goes the ding of my phone. An angel just got its wings. So let me silence that so it doesn't happen again. All right. So now I have to find out the height of these. Okay, so what I need to do to find out the height of these is, like I just said, plug those in. So I have to find out f of 1, f of 2, f of 3, and f of 4. So I'm using the formula that I have. That would be my f of x, right? And so f of 1 is going to be 3 times 1 squared minus 2. 1 squared is 1. 3 times 1 is 3. 3 minus 2 is 1. F of 2 is going to be 3 times 2 squared minus 2. 2 squared is 4. 3 times that is 12. 12 minus 2 is 10. 3 times 3 squared minus 2. 3 squared is 9. 3 times that is 27. 27 minus 2 is 25. And then 3 times 4 squared minus 2. 4 squared is 16. 3 times 16 is 48. 48 minus 2 is 46. Now, the height of all of these respectively is you are 1 unit tall, you are 10 units tall, you are 25 units tall, you are 46 units tall. So basically what I'm doing now is I'm adding up all of these rectangles, all right, knowing their heights, 1, 10, 25, and 46. Okay. Now, how do I figure out the lengths? Well, I know the length because I found the change in x. They're each 1, 1, 1, and 1. So what I'm going to do is I'm going to use that number 1 and multiply that number 1 to all of these and add them up. So 1 times 1 plus 1 times 10 plus 1 times 25 plus 1 times 46, which is 1 plus 10 plus 25 plus 46. Okay, and that will all end up being 82. So what this does is this gives me an estimate of the area underneath the curve between 1 and 5. It's an underestimate though, because as you can see, there's some gaps underneath. And that sometimes is the issue with Riemann sums, where it's never going to be exact, it's going to be approximate. So the approximate area under the curve between 1 and 5 of 3x squared minus 2 is about 82, knowing very well it's actually going to be just a little bit more than that. Riemann sums. Use a midpoint Riemann sum to approximate that guy right there, the integral between 0 and 5 of x squared minus 4 with 5 equal subdivisions. Well, let's find out how poor of an artist I am and try to draw this out to the best of my ability. Okay, I know x squared minus 4 looks like this. I know it's going to go through 2. All right, so a midpoint Riemann sum, okay, means that I'm going to try to estimate where midpoints are and draw like, oh boy, I'm going to be so bad at this, draw like rectangles through the midpoints. That's actually not too bad. It just got real bad. Well, that's awful. But the idea is, kind of ignore the last two, but the idea is I need to find out what the area of all of these guys are. Add them all up. Now the fun part about this guy is you're underneath the x-axis. So you would be like negative areas and you would be positive areas, and we would assume things would cancel out. Now when we do left and right Riemann sums, we use like the left and right endpoints. Now we're going through the middle. So this is going to think, we're going to be forced to think a little extra. You're 5 and we're being asked to find equal subdivisions. So I had to find out how long each of these guys would be if I knew how to draw them all equally. But that's all right. That's easy. So that's like, the change of x is going to be b minus a over n. Okay, if you watch my last 2 videos, you've seen me use this before. What's b? That's the upper limit. What's a? That's the lower limit. What's n? That's how many subdivisions there are. So each of these rectangles are going to be 5 minus 0 divided by 5 units long. So 5 over 5 is 1. So each of these rectangles are going to be 1 unit long. I can handle that. Now what I don't know is how tall they are. Well, the way I find out how tall they are is by plugging in the midpoint. Now, if I know that these are each 1 long and it starts at 0, I have 5 intervals going on from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 5. Now, what are the midpoints between those? The numbers are easy. 0.5 is a midpoint, 1.5 is a midpoint, 2.5 is a midpoint, 3.5 is a midpoint, 4.5 is a midpoint. So how tall are each of these? Well, I have to plug in 0.5. And then 1.5, and then 2.5, and all of that. I'm not going to draw it out, but that'll help me find out how tall each of these rectangles are, and then I can do a little bit of math. So I have to find out what f of 0.5 is, f of 1.5 is, f of 2.5, f of 3.5, and f of 4.5. All right, so we take these functions, we plug it into that f of x right there, and do some math. So 0.5 squared minus 4 is going to be 0.25 minus 4, which is negative 3.75. And then we do it again. 1.5 squared minus 4 is going to be 2.25 minus 4, negative 1.75. So what this is telling me is this guy goes down to negative 3.75. That guy goes down to negative 1.75, and now it's giving me the heights of these rectangles. Okay, I just wanted to remind you that's the point of all of this. what am I doing? 2.25 is, or 2.5 squared, so that would be 625. So 6.25 minus 4 is 2.25. So now we're in positive territory. 3.5 squared minus 4 is going to be, was that 12.125 minus 4, which is 8.25. That's how tall that rectangle is going to be. And 4.5 rather, squared minus 4 is going to be 2025, oh boy, minus 4, which is 16.25. All right, now that's how tall each of these rectangles are respectively. Now what I do is I multiply each of these to the lengths to find out the area. Those lengths are 1. We know that. So 1 times negative 3.75 plus 1 times negative 1.75, and keep doing that, plus 1 times 2.25 plus 1 times 8.25 plus 1 times 16.25. And what that does is that gives us the area. Notice the area of the rectangles under the x-axis are negative. The areas above are positive. That's supposed to happen. They're supposed to cancel each other out to an extent. Not cancel exactly, but the area down here is supposed to cancel out whatever area that we would get up here that's the equal size. Okay, obviously the numbers don't change, so I kind of just wasted my time a little bit, but there's no waste of time on YouTube because it just gives me more YouTube money, baby. So let's write that out. And we're going to pretend like I didn't type that out on a calculator ahead of time and say that this will give us 21.25. All right, so very, very involved. Okay, but you know, that's how you do a midpoint Riemann sum. Fun stuff. Use a trapezoidal sum with 4 equal subdivisions to approximate the integral between 0 and 4 to 3x plus 2 dx. All right, so let's label what we know. Let's label what we have. You would be like my upper limit. You would be my lower limit. Okay, you would be my subdivisions. Your f of x. Okay, if you know my Riemann sum videos, if you've seen those, the beginning is exactly the same for the trapezoidal sum. Okay, the change of x is going to be like if I were to graph this out, right? If I were to graph this out, it's going to look like that. Okay, but what we're dealing here is we're not dealing with writing out rectangles. We're now dealing with trapezoids that we will build to kind of come up with an approximation. All right, that's what we're dealing with here. So what I have to figure out is how long. I know it goes up from 0 to 4. I have to, if I'm using 4 subdivisions, I have to find out how long these are and how tall each end is. Okay, so let's do that. The change of x is going to give us how long these are. So that is calculated by b minus a over n. B is going to be 4. A is going to be 0. N is going to be 4. 4 minus 0 is 4. 4 over 4 is 1. So that tells us each of these are going to be 1 unit long. Okay, so from 0 to 1, 1 to 2, 2 to 3, 3 to 4. What I don't know is how tall each of these are. With Riemann sums, we focused on rectangles. Well, with trapezoidal sums, we're focusing on trapezoids. So I don't just want 4 of them, I want all 5 of them. I want to find out what f of 0 is, I want to find out what f of 1 is, I want to find out what f of 2 is, what f of 3 is, and what f of 4 is. So that's going to be my next step, is to use all of the endpoints to find what I have. Not so much just, some of them. So I'm going to find out what f of 0 is, f of 1 is, f of 2 is, f of 3 is, and f of 4 is. I use that by using that formula right there. 3 times 0 plus 2 is nothing plus 2, which is 2. 3 times 1 plus 2 is 3 plus 2, which is 5. 3 times 2 plus 2 is 6 plus 2, which is 8. 3 times 3 plus 2 is 9 plus 2, which is 11. 3 times 4 plus 2 is 12 plus 2, which is 14. So this end of the trapezoid. That height right there is 2 units tall. You're 5 units tall. You're 8 units tall. You're 11 units tall. You're 14 units tall. Now, if I wanted to, I could take each trapezoid and use the trapezoidal area formula and kind of calculate all 4 of these individually, which wouldn't be the end of the world. But in this case, what I'm going to do is I'm going to use the trapezoidal sum formula, which is going to be the change of x over 2, so 1 over 2, and it's going to be the f of whatever plus f2, f of what. Now, let me actually write out the actual formula first, because it's a gross formula. Let me actually write it out. It's change of x over 2. Okay, and all of this is coming from the idea of the area of a trapezoid, but we're adding a bunch of trapezoids. Okay, the change of x over 2. You will insert f of x sub 0, which means the left guy, plus 2 f of x sub 1s, plus 2 f of x sub 2s, and you work your way all the way until you get to the very end, f of x sub n, and only one of those. Again, this is basically me coming up with the trapezoid formula but adding a bunch of up. Now what this looks like here in this case is since f of x, or the change of x, was 1, it is going to be 1 over 2 like I said. F of x sub 0 would be me plugging that guy in, which is going to be 2, plus 2 times f of x sub 1 would be me plugging in 1, so 2 times 5, plus 2 times 8, plus 2 times 11, and then the very last one doesn't get multiplied by 2, it's just 14. Okay, this gives me the area of all of the trapezoids. Okay, 2 plus 5 plus, so again, 1/2 of 2 plus 5. 1/2 of 5 plus 8. And so 5 is being used twice. 8 will be used twice. That's why these are 2's. All right? When you do all that, you get half of 2 plus 10 plus 16 plus 22, the Taylor-Swift special, plus 14. All of these numbers on the inside add up to 64, so half of 64 is going to be 32. And based on the picture that I drew, that is going to be an extremely accurate, if not an exact answer. Okay, so trapezoidal sum, wacky stuff, but fun. The velocity of a car is measured at intervals of 1 second as shown in the table below. Use a left Riemann sum with 4 intervals to approximate the total distance traveled over the first 4 seconds. So here's my first 4 seconds. If I wanted to focus on the left-handed Riemann sums or the left-handed points, it would be these numbers right here. Now it's 4 seconds with 4 intervals. So if I were to use the change of x formula, which is b minus a over n, you would be my a, you would be my b. Okay, my n is 4. So 4 minus nothing over 4 is 4. So that's my change of x. Now what I do is I take those left-handed points and I find out what, in this case, v of 0 is, v of 1 is, v of 2 is, v of 3. If I were to use right-handed ones, I would use 1, 2, 3, 4. If I were to use midpoints, I do 0.5, 1.5, 2.5, 3.5. But I'm using the left-handed, so those are my left-handed points. I have my numbers already, 0, 3, 5, and 6. How lovely. Now, what I do is, oh, I forgot to divide that by 4. Oopsies, 4 over 4 is 1. Silly me. All right, so now that I have all that information, I have everything I need. I'm going to build my Riemann sums and say that I'm going to use that number times 0 plus that number 1 times 3 plus that number 1 times 5 plus that number 1 times 6, which is 0 plus 3 plus 5 plus 6, which is going to be 14. Yeah, Riemann sums on a box. Kind of strange, but I like it. Which definite integral is represented by this summation? Well, this is summation notation, and basically it takes the idea of Riemann sums and it takes the idea of adding up a bunch of areas and turns it into an integral which is supposed to look like that. Since we start at 1 and end at 6, we start at 1 and end at 6. And since I have 2i squared plus 1, it's going to be magically transformed into 2x squared plus 1, and we'll put that in parentheses, and you always attach a dx to the end. So in this case, this guy is going to look like a. What is the definite integral notation of the following? You have sigma notation with a limit as n approaches infinity. You start at 1, you end at n. All of this terrible, terrible, terrible stuff. All right, so this is what we've got going on. We've got ourselves a 3i over 2. All of it is going to be squared. You got a 6i over n. Okay, when you're dealing with sigma notation, first off, let's apply that squared. So we have sigma n I equals 1, limit as n approaches infinity. Let's apply that squared so you become 9i squared over 4. You become still 6i over n. Now when you're dealing with sigma notations, when you sigma this, okay, any I becomes x. When you sigma I over n, it becomes 1. Okay, so what's going to happen here is if we just make believe that sigma is attached to both, let's get rid of all this limit stuff and just read it. Just let's simplify it and rewrite it like this, just to make life easy. Okay, sigma, sigma. Okay, rip out a 9 over 4. 9 over 4 is sigma I squared. Okay, rip out a 6, sigma I over n. Okay, once you have that, we can now kind of apply these rules here. The sigma of I squared is going to be x squared, so you become x squared with a 9 over 4 attached. You become 1, so plus 6 times 1 is 6. When I look up here, the only one that applies to that is going to be C. So C is going to be my answer. Okay, now the reason why we have 0 and 3 is because of the way that this is graphed. If you were to graph this and do a little bit of solving, you would have just an integral between 0 and 3. But yeah, it's kind of sigma notation when it deals with these limit things are kind of gross. But that's what we get here. Fun stuff. Which of the following expressions is equal to the limit as n approaches infinity of this monstrosity? All right, so we're kind of comparing this stuff to sigma notation. I'm comparing this to what essentially is this. Limit as n approaches infinity of the sigma from whatever, k equals 1 to infinity, right? And it's always going to be b minus a over n. And then we have times f of a plus b minus a over n k. Okay, now this is normally supposed to be f of x, so this whole thing is x. When I look at this and I see 1 over n and I'm comparing 1 over n to b minus a over n, that tells me that b minus a is 1. Okay, so we're dealing with a change. Remember, integrals look like this. The difference between b minus a is going to be 1. So that knocks u out of the question. Okay, so at least we can pull that off. Now what I also know is b minus a is 1. So my x is going to look like, some a, which by the way, if all of these look like that, that tells me right there that a is 1, a is 1, a is 1, a is 1, which means u are going to be 1, and if b is going to be 1 more than that, 2, which knocks u out of the question. Now what I have to do is figure out, okay, well, hold on, x is going to be a, which is 1, plus 1 over n times some k. Well, here we are, and that k is going to be 1, so hold on, so if k is 1 and it starts out there, and k is 2 and it starts out there, right? I basically have everything I need. So if you're going to be 1 and you're going to be 1, that is exactly x. So my f of x is going to be e to the x. I'm not going to add 1 to it. I'm perfect. I'm there already. So this ends up being B because of all the little bit of math stuff that I could do to find out that it's B. Confusing? Yeah. Easy? No. But that's how I would do it. I approached it a little differently, and I kind of like it. What is the best interpretation of the integral antiderivative capital F of x equals the integral from a to x of f of t? Well, the antiderivative gives you the area under a curve from 0 to x, which is the answer B. Okay, so this is just basically a very initial definition of what the integral does for us, and the integral gives us the area under the curve. Capital F is the antiderivative notation. And that's what you do for this one, short and sweet. If g of x equals the integral from 2 to x of 3t squared minus 4t dt, what is g prime of x? Well, the fundamental theorem of calculus states that a capital G of x would equal the integral of whatever this is. I guess we can call it from a to x of f of t dt. So that's what this is. Now, if this is g of x, if we're calling it lowercase g of x, then fine, I'll call it lowercase g of x, whatever. But taking the derivative of it essentially has me take away the integral. And what I'm going to be left with is I'm going to be left with, instead of 2 to x, I'm going to be left with the exact equation that I started out with, but with x's instead. That guy right there. So the answer is going to be A. Fundamental theorem of calculus. Kind of useless, but it's there. If h of x equals the integral from 1 to x of 2x plus 3 dt, what is h prime of x? Well, we're going to use the fundamental theorem of calculus here. And the fundamental theorem of calculus states that if I were to have the antiderivative, that's going to be the exact same thing as the derivative from sum a to x of f of x dx, right? Well, they're calling it lowercase h, so fine, let's call it lowercase h. But if I were to take the derivative of that, let me write it out. If I were to take the derivative of that, that essentially cancels out the integral. And what I'm left with is 2t plus 3, and instead of t's, I have x's because I'm using of x. So 2x plus 3. It's going to be A. Given the graph of f above, let g of x be the integral from 0 to x of f of t. So note that the area A is 5, area B is 8, and C is, oh, I don't have C. But it's asking me for the value of g of 7. So the value of g of 7 is going to be me saying g of 7 is now the integral from 0 to 7 of this f of t dt. Now, what you're being asked to do is find the area under the curve from 0, which is u, to 7, which is u. Any area above the x-axis is a positive area. So any area under the x-axis is a negative area. So you are actually not going to be 5, you are negative 5. So the area under the curve isn't me doing 5 plus 8. It's actually me doing negative 5 plus 8. Because whatever area is down here is going to cancel out the same amount of area up here. And so at the end of the day, my answer is going to be 3 here. Kind of tricky. The graph of the function f shown above has zeros at 0, 4, and 6, and has horizontal tangents at 2, I can see that there, and 5, I can see that there. Let g be the function defined by its integral. Oh, so I don't even see g. So g is the integral from 0 to x of f of t. For what values of x is the graph increasing and concave down? So this is the graph of f, right? This is the graph of f. So what I'm thinking is fundamental theorem of calculus thoughts. What I care about is I care about g prime of x, and that will get me the increase-decrease part. Okay, so if it's asking me for increasing, I would normally take the derivative and find out where the derivative is positive or negative. Now, I want increasing, so I care about where g prime of x is positive. Well, what's g prime of x in this case? G prime of x is going to be the derivative of the interval. So it's going to be just the interval's gone now, and I'm left with f of x. That's what the fundamental theorem of calculus says. So I care about where f of x is positive. So if this is the graph of f of x, I care about where f of x is above the x-axis. And f of x is above the x-axis between 4 and 6. Now, in order for me to find concavity is going to be CU, CD. Concavity is going to be the second derivative. And I want it to be concave down, so I care about where the second derivative is down. Now, the second derivative would be me like going up here and saying, all right, so g double prime of x is going to be f regular prime, and I care about when that's less than 0. The derivative of a function means slope, so I care when the slope is negative, or when f of x is decreasing. This is f. F of x is decreasing from 0 to 2 and decreasing from 5 to 6. So that guy is going to be from 0 to 2, union, 5 to 6. Where do both of these happen at the same time? Well, if one of them happens from 4 to 6, then 0 to 2 has nothing to do with what I'm doing up here. This is from 5 to 6. So 5 to 6 compared to 4 to 6 means that all the magic happens between 5 and 6. Because that's where it kind of intermingles, if you will. If you will. And that's how you do it. Fun stuff. What is the integral from 1 to 3 of f of x? Well, we know that the integral from a to b of f of x is going to be the antiderivative from b at b minus the antiderivative at a. I'm given this information right here. So if I want from 1 to 3 of f of x, it's going to be f of, u would be my a, u would be my b, f of 3, capital F, minus capital F of 1. So let's see if I have that information. 1 goes to 3, and 3 goes to 8. So this becomes 8. F of 3 is 8 minus F of 1 is 3. And 8 minus 3 is 5. Baby. Fun stuff. All right, so the integral between a and b of f of x of d of x is 3. The integral between b and c of f of x is -2, and, you know, everything is in between a and c. What does the integral of a to c equal? Well, by definition, if you take the integral and your upper limit is a and your lower limit is, or I guess your upper limit is c and your lower limit is a, common sense would tell us that the integral, and let me just really make this lazy, the integral of f of x dx from a to c is going to be the same thing from a to b, and also including b to c, which makes sense. I mean, you know, I don't know what these areas are, but if I were to show this graphically quickly, we have 3 and -2, so maybe you have a graph that looks like this, your 3, your 2, your A, your B, and your C. It would make sense that from A to B and B to C is going to be A to C. So knowing that, we can say that f of x is 3, okay, or I'm sorry, A to B is 3, A to C is -2, and adding those guys together, you get a big fat 1. Okay, so pretty standard type of problem that's, hey, let's understand the rules of integration type thing, and that's us understanding the rules of integration. Fun stuff. The function f, continuous for all real numbers x, has the following properties. The integral from 1 to 3 of f of x dx is 7. The integral from 1 to 5 of f of x dx is 10. what is the value of k if the integral from 3 to 5 of kf of x dx is 3? Well, first off, I need to find out what the integral from 3 to 5 of regular f of x is before I could even consider that. Just a little bit of lazy notation. Common sense would tell us that the integral from 1 to 5 is going to be the same thing as the integral from 1 to 3 plus 3 to 5. Okay, so what I have so far, what I know is that from 1 to 5 it's 10, from 1 to 3 it's 7. So the integral from 3 to 5 of f of x dx, me using my proper stuff, is going to have me subtract 7, cross u out, and the integral from 3 to 5 of f of x dx is going to be 10 minus 7, which is 3. All right? So if I wanted to, I could rip that k right out of there, because I can, because it's a coefficient, doesn't affect the integral. The integral of k times the integral of 3 to 5 of f of x dx is 33. I just found out that this guy right here is 3. So k times 3 is 33. Or 3k equals 33. Divide both sides by 3. Divide both sides by 3. K is going to be regular 11. So my answer is going to be E, baby. Given that the integral from negative 2 to 2 of f of x dx is nothing, and the integral from 0 to 2 of f of x dx is 6, use the properties of definite integrals to find the integral of 0 to negative 2 of f of x. Well, this is going to be fairly nice, okay? But let's try to draw ourselves a picture. What do we know? Well, from 0 to 2, I have some area that is 6, okay? So that's from 0 to 2. Everything starts out here at negative 2. All right, so all of this is going to add up to 0 when I figure that out. And that's almost too much common sense, but let's just go a little bit further. The integral from negative 2 to 2 is going to be the same thing, and I'm just using very lazy notation. I'm going from negative 2 to 2, so it makes sense that negative 2 to 0 plus 0 to 2 is going to give me negative 2 to 2. Negative 2 to 2 is nothing. Okay? Negative 2 to 0 is, I don't know. But I do know that 0 to 2 is 6. So if I subtract 6 from both sides and clean up the way this is supposed to be worded, all right, you're gone. I could say the integral from negative 2 to 0 is of, what is this, f of x dx is going to equal 0 minus 6, which is negative 6. Circling my answer would be wrong. Why? Well, because it's not giving us that. The limits are flip-flopped. Oh, so if I have flip-flopped limits, it's a simple fix. Flip-flop the limits like we have up here, and then while you're at it, just take the opposite of the area. So negative 6 is positive 6. Tricky, tricky. Tricky, tricky, tricky. So I think many people wouldn't really think about it and say the answer is negative 6. But that's because the integral and its limits are in the correct order. We were given it out of order. We were given to us backwards, which means our answer is going to be opposite. Gotcha. Given the graph of f of x above, note that area A is 5, B is 8. So you are 5, you are 8. We care about stuff between 11 and 0. Seems kind of backwardsy. I'll deal with that in a minute. We don't know the area of C. Well, that stinks. Oh, but you know what I can do? I noticed that from 7 to 11 gives me this base of 4. I notice that from 0 to 4 gives me a height of 4. This is a perfect triangle. So the area of this guy right here is going to be half of base times height, or half of 4 times 4. Half of 4 times 4 is going to be 8. So you're 8. All right. So the integral from 0 to 11 is going to be this 5 underneath the x-axis. So if it's underneath the x-axis, it counts as negative 5. This 8 above the x-axis, and this 8 above the x-axis. So that's 3 plus 8, which is 11. Yippee! So the integral between 0 and 11 of f of x dx is 11. Circling that would be a dire mistake. Why? Because they want you to find from 11 to 0. Remember how I noticed that seemed all backwardsy? Well, it's because it is. Easy fix though. If the integral from 0 to 11 is 11, the integral from 11 to 0 is the opposite of it. So negative 11. Lots of 11s here. That's how you do it, though. Fun, fun. Evaluate by drawing a graph of the integral negative 2 to 3 of the absolute value x plus 1. All right, so by definition, when you integrate something, you are finding the area under a curve. And in this case, we are going to have a v. So this has me shift left 1 unit, and I'm going to draw myself a perfect V. I'm going to go to the right all the way to 3. So there, right? See that perfect line there? And I'm going to go to negative 2 in the opposite direction. My job is to find the area underneath the whole thing put together. All right, so I'm giving myself a black triangle and I'm giving myself a red triangle. All right, now this black triangle is 1 unit long and 1 unit tall, and it's a triangle. So the area of the black triangle is going to be half of base times height, or half of 1 times 1, or half. You with me? Of course you're with me. Now this triangle has a length of 4 and has a height of 4. So the area of that guy is half of base times height, so half of 4 times 4, which is going to be 8. Adding these two together is going to be 1/2 plus 8, which is going to end up giving me 8.5. So again, the integral is going to give you the area under a curve. I had to draw myself a curve in this case, find the area by using stuff I learned back in like 6th grade, and then found an answer of 8.5. Wasn't that neat? All right, we finally are getting to the definite integral and doing things the way it's supposed to be done and intended. We have ourselves a regular term, so it's kind of like power rule stuff. For power rule stuff, if I give you the integral, okay, and I'm just going to use very, very, very basic stuff, x to the nth, what you do, dx, what you do is you have 1 over n plus 1 x to the n plus 1. So the first thing that I have to do here is use this power rule to integrate x squared. All right, so if I were to really show my steps, and I'll do this for this video, my n is 2. I'm going to do 1 over 2 plus 1, x to the 2 plus 1. Now I still have my limits of integration that I'm going to write out over here, and those limits of integration are going to be between 1 to 3. Doing a little bit of work, I have 1/3, x to the 3rd power, limits of integration. Now, since I have these limits of integration, we have to do the whole subtraction thingy that integrals do. So what you do is you write out what you got, 1/3, okay, but instead of saying x cubed, you plug in your upper limit. So 1/3, 3 cubed, close my bracket, minus 1/3, 1 cubed, close the bracket. And again, this comes from the idea of the antiderivative of the upper limit minus the antiderivative of the lower limit. And that's what I did. I rewrote this out, plugged in 3, rewrote this out, plugged in 1, subtract the one from the other. So it's just a little bit of math now, which is what this is. 1/3 times 27 minus 1/3 times 1, 9 minus 1/3 is going to equal 8 2/3. Okay? Fun stuff. Compute the definite integral where we have the integral between 0 and 1 of e to the x dx. Well, this is a fun little rule. The integral of e to the x dx is just e to the x. So what I do is I take the integral, e to the x, I carry along my limits of integration, which are still just 1 and 0. Remember the rule, when you integrate and you have limits of integration, you take the antiderivative, which I just did, right? Plug in the upper limit, plug in the lower limit, subtract the upper one minus the lower one. So in this case, I have e to the x, upper limit is 1, so e to the first power minus e to the x, plug in the lower limit, e to the 0 power. E to the first is e, anything to the 0th is 1, e minus 1 is going to be our guy. Compute the definite integral, the integral between 0 and pi of sine x dx. The integral of sine x is not cosine. That's the derivative. The integral of sine x is negative cosine. Now we're going to carry along our limits of integration, which are 0 and pi. Remember, when you integrate and you have an upper and a lower limit, you take that antiderivative, which I just did, plug in the upper limit, minus, take the same thing, plug in the lower limit. That's what I'm going to do here. I'm going to say negative cosine of the upper limit, which is pi, minus negative cosine of the lower limit, which is 0. Okay, the cosine of pi is negative 1, so negative negative 1, minus the cosine of 0 is going to be 1, so negative 1. Negative negative 1 is 1, negative negative 1 is 1, 1 plus 1 is 2. The answer is A, baby. Compute the definite integral. Well, we have the definite integral between 1 and 4 of 1 over x dx. The integral of 1 over x is ln of x. So this becomes ln of x, and my limits of integration are between 1 and 4. Now remember the rule, whenever you take the integral of something, you take that antiderivative, you plug in the upper limit, and then you plug in the lower limit, subtract the one from the other. So what I'm going to do is I'm going to write this out and plug in 4. So the ln of 4 minus the ln of 1. Fun fact, the ln of 1 is 0. So that just leaves you with the ln of 4, and that's going to give me A. Fun stuff. Compute the definite integral between 1 and 3 of 2x cubed minus 5x squared plus 4. Whenever you're taking the power rule and the integral, the rule looks like this. All right, if you're given, let's throw a letter in there, so cx to the nth dx, you're going to keep that c just kind of lingering there, okay? And then you're going to have 1 over n plus 1 x to the n plus 1, and then plus some arbitrary constant that we're not going to worry about right now. So what this is going to look like, okay, is this first term is we're going to keep the t lingering, or the 2 lingering right there. My n is 3, so 1 over 3 plus 1, x to the 3 plus 1. Okay, that's that guy. Let's do this one. Minus 5. My n here is 2. So 1 over 2 plus 1, x to the 2 plus 1. Okay. Now, if you're given just a constant, just attach x. Don't overthink it. So let's clean this. Oh, and by the way, with all of this, I still have my limits of integration of 1 to 3. I can't forget that. So let's clean this up. All right. This will be 1/4. So 2 times 1/4 is a half. X to the 4th power. Minus, this will be 1/3, so minus 5/3, x to the 3rd, and then plus 4x is much more manageable. Limits are 1 and 3. Now remember, when you're taking the definite integral, you find the antiderivative, which is that guy right there. You plug in the upper limit, you plug in the lower limit, subtract the one from the other. So I'm going to plug in 3, so 1/2, 3 to the 4th, minus 5/3, 3 cubed plus 4 times 3. Then we're going to do the same thing, minus, do the same thing, plug in 1. So 1/2, 1 to the 4th, minus 5/3, 1 to the third, plus 4 times 1. Okay? And just some gross math. 3 to the fourth is 81. 81 over 2 is just 81 over 2. Minus, that's going to be 27. So negative 5/3 times 27 is the same thing as negative 5 times 9. So negative 45. I don't know why that took me so long. And then plus 12, I can handle that. Minus, all of these become 1, so are basically useless. So a half minus 5/3 plus 4. All right. And we're still moving. And we're still moving. 81 over 2 minus 45 plus 12 is going to be 15 over 2. One half minus 5/3, 6 plus 4, 13 over 6. 17 over 6. Combining these is going to get you 14 over 3. Which is none of these. I don't know why I do that. I don't know why I kept that up there when I should have deleted that, because that's absolutely not true. So we'll pretend that that's not even there. But yeah, that's going to be my answer right there. None of those, none of those, none of those. Thank you, ChatGPT. You're letting me down again. Evaluate the integral between -2 and -1 of 4 over x squared. Well, let's rewrite this to the integral of 4x to the -2. Much better. And then we could use that power rule that says if I give you something that looks like this, right? If I give you something that's like x to the nth, when you integrate that, that becomes 1 over n plus 1 x to the n plus 1. So when we see something that now looks like that, we're going to kind of rip 4 out, okay? And then we're going to do 1 over, u would be my n, so 1 plus -2, so 1 minus 2, x to the 1 plus -2, so 1 minus 2. We still have our limits of integration, and those limits of integration are still going to be -1 and -2, but not in that order. I can't forget. All right, so this is going to simplify out to 1 over 1 minus 2 is -1. So 4 times -x to the -1. Limits are -2 to -1. Let's rewrite that out one more time. Let's drop x to the -1 to the bottom and bring that negative out. So -4 over x, with my limits being -2 and -1. Okay, let's plug stuff in. That's going to be, and remember the rule. Remember the rule, right? This guy. So we're going to plug in our upper limit. We're going to plug in our lower limit, subtract the one from the other. So the upper limit is going to be -4 over -1 minus -4 over -2. So negative over a negative is a positive. You just become 4 minus triple negative, so it's going to stay negative. 4 over 2 is 2, right? And you just get 2. Pretty nice. Evaluate the integral from 1 to e squared of 1 over x. Well, the integral of 1 over x is ln of x. And then the limits of integration come along for the ride. Remember, after you integrate, you take the antiderivative that we just found, plug in the upper limit, plug in the lower limit, subtract the one from the other. So what this is going to look like is ln of the upper limit, so ln of e squared, minus ln of the lower limit, which is 1. Ln of e squared is just 2. Ln of 1 is nothing, and 2 minus 0 is 2. All right, now we have ourselves regular old indefinite integrals. No, you don't have to worry about stuff like this anymore. These problems are a whole lot friendlier. We just have to add a little extra to it. Okay, so when you look at the integral of 4x to the third, you're thinking, all right, well, let's rip that 4 out and then focus on x to the third dx. Okay, 4 is still there. You are going to say 1 over the exponent, which is 3 plus 1, x to the 3 plus 1. Now, what makes indefinite integrals different is I don't have limits of integration. So at the very end of every single indefinite integral problem, we have to add an arbitrary constant. We don't know what that constant is. We just know it's there because if we were to then take the derivative of this guy, the constant becomes 0. So you become 4 times 1/4 x to the 4th plus c. You guys cancel out to get me x to the 4th plus c, which gives me a. Don't forget that plus c. Very easy to do. Evaluate the indefinite integral of 5e to the x dx. Well, this isn't an indefinite integral, which means I don't have to worry about limits of integration. I don't have to worry about stuff like that. That's dead to me, at least for this section it is. I'll rip out that 5, and I'll just integrate e to the x dx. Well, this is nice. The integral of e to the x dx is just e to the x. However, when I'm taking the indefinite integral, I have to add some arbitrary c. Why? Well, if I were to take the derivative of this to try to go backwards into that c would become nothing. So I need that c there. So in this case, my answer is going to be a. Evaluate the indefinite integral of 3x squared minus 2x. If I wanted to be fancy, I just rip these two apart, like I'm doing right now. And so I will, because I said I would. And as you do more of these, you'll find out maybe this step is not so much necessary. If I want to, I can rip out a 3, so I'm left with that. I can rip out a 2, so I'm left with that. And as I do more of these, you'll realize that that part is also unnecessary. Now we integrate using our power rule. 3 just lives there. Okay, you're going to be 1 over 2 plus 1, x to the 2 plus 1, right? Minus 2. And you're going to be 1 over 1 plus 1, x to the invisible 1 plus 1. Now, when you do the indefinite integral, you have to remember to add an arbitrary c at the very end. Okay, since we're not doing the f of b minus f of a thing, we have to do this. Now we simplify 3 times a third, x to the third, minus 2 times a half, x squared. Beautiful things happen. You cancel out, and you're left with x cubed minus x squared plus c. And as you do more of these, you might be able to skip some of these steps, and you'll find out things that are a little bit faster. But right now we're at the very beginning, which is a very good place to start, and we're just making sure we show all of our steps. Plus, gets me more YouTube money with my more time and stuff. Speaking of which, like and subscribe. Evaluate the indefinite integral. Well, let's rip out a 6, because why not? And that leaves me with the integral of sine x dx. The integral of sine x dx is going to be negative cosine x. And you know what? Since this is an indefinite integral, we can't forget that little plus c that's hanging out at the end. Let's combine these, put these guys together, make it a little bit prettier looking. And once I do that, I am left with b, and thus and therefore b is my answer. Evaluate the integral of 1 over 2x dx. Well, let's rip out a half. Let's rip out a half, shall we? So the half of the integral of 1 over x dx. Oh, the integral of 1 over x is ln of x. Now, whenever I take the indefinite integral, I can't forget about my little plus c that's got to be hanging out at the end. But that's it. That's all we can do here. That's going to be my guy. Fun stuff. Evaluate this indefinite integral 3 over secant x dx. Well, I don't like the way that looks. I don't like secant just hanging out there. Let's bring it up there and call it cosine. Like that. While we're at it, let's rip out that 3 because we can. As you do more of these, you'll realize that stuff like that's not necessary. Maybe you can skip that step. But now I have the integral of cosine. Gross, 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 gross. Find the antiderivative of f of x, which is bleh. Well, that's just me finding the indefinite integral. So I'm going to write out 3x to the 8 over 9 plus 5x to the 2 over 7 dx. I'm going to split these up into two separate integrals because why not? So 3x to the 8 over 9 dx plus 5, or well, I'm jumping the gun, 5x to the 2 sevenths. Now while I'm at it, oh, dx, can't forget that. While I'm at it, let's rip out a 3, like that. So I have x to the 8 ninths dx. And let's rip out a 5. X to the 2 sevenths dx. So this is the rule, okay? For this one, leave 3 there, right? Do 1 over your exponent plus 1, so 8 ninths plus 1, and then x to the 8 ninths plus 1. We're going to do the same thing here. Let 5 linger, and maybe I should put this in parentheses because that just looks sloppy. Plus sign. Let 5 linger, like that Cranberry song. And then you're going to put 1 over 2 sevenths plus 1, x to the 2 sevenths plus 1. Now, since this is an indefinite integral, we cannot forget our little plus c at the end. So let's not forget that. 3 is still 3. Okay. 8 ninths plus 1 is 17 ninths. So 1 over 17 ninths, x to the 17 ninths. Plus 5. 2 sevenths plus 1 is 9 sevenths, so 1 over 9 sevenths, x to the 9 sevenths. Did I say that upside down? I did. I wrote it upside down, but I said it correctly. 9 sevenths. Wait a minute. Did I? I don't remember. I don't remember, and I'm not going to go back and edit this anyway, so I don't think people make it these far in my videos. I try. Comment if you do. All right, so that's gross. So reciprocal stuff, 3 times 9 over 17, x to the 17 over 9, plus 5 times reciprocal 7 over 9, x to the 9 over 7 plus c. And let's finish this puppy up by multiplying 3 to 9, 27 over 17, x to the 17 over 9 plus 35 over 9, x to the 9 over 7 plus c. Definitely not the prettiest one out there, but I think I did it right, so I'm sticking with it. The indefinite integral of cosine x minus 3x squared plus 3x. Well, we could rip this out into 3 separate integrals if I want to. So I have the integral of cos x dx minus, why don't I rip out that 3? Integral of x squared plus, oh, I forgot my dx, can't forget that, plus the integral of 3 dx. And we'll do each one step at a time. The integral of cosine is sine. Minus 3. The integral of x squared is going to be 1 over 2 plus 1, which is 3, x to the 2 plus 1, which is 3, plus the integral of a constant has me attach an x, and at the end of all of this we have plus c. Can't forget that. So sine x, you cancel out, minus x cubed plus 3x plus c is going to be my guy, baby. Nifty, nifty, nifty. Integration by U substitution. If you're looking at your integral and it looks all chain rule-y or all product rule-y or all quotient rule-y, it's probably not something that you can do straight up. Now I know I can FOIL this guy out a bunch of times and distribute 2x, but what fun is that? It's not. So this is what you do. You look at the two functions that you have, 2x and x squared plus 1. And you try to find something that looks like its derivative is floating around. It looks like x squared plus 1's derivative is floating around over here. So whatever looks like its derivative is floating around, you're going to call it u. So u is going to equal x squared plus 1. Take the derivative of that. du dx is going to be the derivative of x squared, which is 2x plus 1, which is nothing. Now, this is how I do it, and I know different teachers do it differently, but this is how I do it. I like to multiply both sides and divide both sides by the dx and the 2x respectively and simultaneously. So what you get would be du over 2x equals dx. Now what I do is I replace what I called u and I take this new dx and plug that in as well and integrate with respect to u. So I have the integral of 2x, x squared plus 1 is u, so u, to the third, and dx is now du over 2x. And if you're like, whoa, 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 how am I going to pull this off? Check this out. The 2x and the 2x cancel each other out. So now we're going to take the integral of u to the third du. The integral of u to the third is going to be 1 over 3 plus 1, which is 1/4, u to the 3 plus 1, which is to the fourth, and I'm going to attach a plus c there. Now I'm not done, because my original problem didn't contain u. I called u x squared plus 1, so I need to plug back in x squared plus 1, so I get 1/4 x squared plus 1 to the fourth power plus c, which is going to be b. All right? Use substitution. Fun, 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 fun for the whole family. Evaluate the integral e to the 3x dx. Now this looks very chain rule-y. And when you integrate something that looks like chain rule, you have to think u substitution. So what you do is you choose a u that appears to have its derivative or something close to it lingering around. Well, there's not many choices here. 3x is going to be my u. So I'm going to call u 3x because when I take the derivative of 3 to the x, or 3x, my x goes away. So take the derivative of u, so du dx equals regular 3. I like to simultaneously flip-flop the dx and the 3, so du over 3 equals dx. And now what I could do is I could take that guy, and the fact that I have that guy, and plug a bunch of stuff in. All right, I called 3x u's, so the integral of e to the u, and I called dx du over 3. And now all is fair. If I wanted to, I can rip out a 1/3, so I have the integral of e to the u du. The integral of e to the u is just e to the u, so 1/3 e to the u. Don't forget your arbitrary c, that's got to linger there. And I'm not going to circle this because u is not in the original problem. So I have to bring back the fact that I called u 3x. So this becomes 1/3 e to the 3x plus c, which is going to be a. Evaluate the integral of 2x over x squared plus 1 dx. Well, this looks like quotient rule, but there's no such thing as quotient rule for integration. So what we do is we use u substitution. We choose a u that looks like its derivative is lingering around. It looks like the derivative of x squared plus 1 is lingering around up here, so I'm going to let u equal x squared plus 1. Now, take the derivative of that. du dx is going to equal 2x plus nothing. Flip-flop the dx and the 2x, and you get du over 2x equals dx. Now I can take what I have right here, I can take what I said right here, and I can take what I found out here and put it all together. The integral of 2x over regular u dx becomes du over 2x, and oh happy day, the 2x's cancel out. So that leaves me with the integral of 1 over u du. The integral of 1 over u du is ln of u. Don't forget your arbitrary plus c. Now, I can't just circle this because u was not in the original problem. I called u x squared plus 1. So I have to substitute back in x squared plus 1 into u. And I have ln of x squared plus 1 plus c. My answer is going to be A for this one. Pretty exciting stuff. Evaluate the integral from 0 to 3 of 2x over the square root of 9 minus x squared. Well, this looks like quotient rule and chain rule mixed into one whole terrible problem. What you do if you have something like this for integration is you choose a u that looks like its derivative is somewhat lingering around. It looks like if I take the derivative of the stuff inside the square root, I get something awfully close to 2x. So I'm going to let u equal 9 minus x squared. Take the derivative of that, du dx is going to equal negative 2x. Flip-flop the dx and the negative 2, and you get du over negative 2x equals dx. Now let's take this guy and substitute all this stuff and do some integrating with respect to u. Now keep in mind, my limits of integration are still 0 and 3, but those happen to be with the x values, not with these brand new u values. Okay? So I'm going to write out 2x over the square root of u, and then dx becomes du over negative 2x. Oh, happy day, the 2x crosses out. I can bring out this whole negative. Now, while I'm at it, this is what I have now, and it's not pretty. I don't like that. So I'm going to kill two birds with one stone right here. Okay, I'm going to move that upstairs and call it u to the negative 1/2. U to the negative 1/2 du. All right, now my limits of integration are still 0 and 3. I can't forget that. And again, those have to do with x, not with u. We'll deal with that when we have to deal with that. Negative is lingering. Okay, u are going to be 1 over negative 1/2 plus 1, which is a positive 1/2. U to the negative 1/2 plus 1, which is positive 1/2. My limits of integration are still going to be 0 and 3, but with the x's. Okay, so let's clean this up a little bit. Let's bring that 1 over 2, flip it and multiply it to the top to get you negative 2. Let's rewrite this back as the square root of u, with my limits of integration being 0 and 3. But again, my limits of integration are 0 and 3 for the x, not the u. What does that mean? I have to substitute that guy back in for u. So that's going to look like negative 2 times the square root of 9 minus x squared with limits of integration at 0 and 3. This is where we do the whole antiderivative of b minus antiderivative of a thing and set up my brackets and do negative 2 square root 9 minus 3 squared, like that, minus bracket negative 2 square root 9 minus 0 squared bracket. The left one becomes negative 2. Probably should move that out there. Negative 2 square root of 0. Big square root, little number. Minus negative 2 square root of 9 minus 0. So you just completely go away. And we have a double negative, 2 times 3, which becomes positive 6. Interesting problem. Evaluate the integral between 0 and pi over 2 of sine 2x dx. Now, whenever you see something that looks like chain rule, you are thinking u substitution. All right, we're going to let u equal 2x here because taking the derivative of that leaves no x's, and that makes life easy. So du dx is going to be just 2. Swap the dx into 2 to make it du over 2 equals dx. Now we can take this guy, this guy, this guy, put some stuff together, and do some integrating with respect to u. So 0 pi over 2, okay? Sine is still sine, but now it's of u. Dx now becomes du over 2, right? What I can do is I can rip out a half. So a half of the integral between pi over 2 of sine u du. Okay, the derivative of sine is, careful, negative cosine u, right? That 1/2 is still lingering. Now my limits of integration are 0 and pi over 2, but remember this 0 and that pi over 2 goes with the original problem where it's x is e0 and x is pi over 2. So I have to substitute 2x back into u. So this becomes 1/2 negative cosine 2x, and now we're cooking with gas. Okay, limits of integration, let's do the whole thing where we make a big bracket. I have 1/2 negative cosine of 2 times pi over 2, close it, bracket it, minus 1/2 bracket negative cosine 2 times 0, close it, bracket it. Okay, you become, I really don't need that first bracket anymore, 1/2 times negative cosine of regular pi minus 1/2 times negative cosine of nothing. Cosine of pi is -1. So negative cosine of pi is +1 minus 1/2. Negative cosine of 0, well, cosine of 0 is 1, so negative cosine of 0 is going to be -1. So we have 1/2, double negative plus 1/2, which last time I checked gives us a whole. And that's what we get. Tricky. Fun. Evaluate the indefinite integral of 4x e to the x squared. So this looks like chain rule stuff. And whenever you're integrating stuff that looks like chain rule stuff, you have to pick a u value that looks like its derivative or something awfully close to it is lingering. If I let u equal x squared and take the derivative of x squared, I get 2x, which is close to 4x. So u is going to be x squared here. Take the derivative of that, du dx is going to equal 2x. Flip-flop the dx and the 2x to get du over 2x equals dx. All right, let's combine some stuff, put some stuff together. We have the integral of 4x e to the, let me see, u now. Instead of dx, I have du over 2x. Well, this is nice. The x's cancel out, which it needs to do. And then 4 over 2 simplifies out to a 2, and we'll put the 2 out here. So I have 2 times the integral of e to the u du. The integral of e to the u is e to the u, so 2 e to the u plus some arbitrary c. I'm not going to circle this, though, because originally I didn't have a u. I had x squared, so I have to substitute back in x squared. So 2e to the x squared plus some arbitrary c. And that'll do it. Evaluate the integral of the cosine of the ln of 4x over x dx. Well, we have stuff living inside this cosine, and that stuff happens to be ln of 4x, so let's let that be my u because we're doing integration by u substitution. So u is ln of 4x. The derivative is going to involve chain rule. No big deal. Take the derivative of the outside, which is 1 over stuff, keep the inside, but then multiply everything by the derivative of the inside, which is 4. So the 4 comes up here. 4 over 4 simplifies to 1 over x. Easy peasy. Let's take that guy, du dx equals 1 over x. Do some cross multiplying and find out that we get x du equals dx. Now let's take this guy right here, this guy right here, this guy right here, and put some stuff together. We have the integral of cosine of, I called ln of 4xu, so cosine of u over x. Instead of dx, I'm calling it x du. Oh, how nice! The x's will cancel out. Oh, isn't that lovely? So now I'm left with the integral of cosine u du. The integral of cosine is sine, so sine u plus some arbitrary c. And since I wasn't given u to start out the problem, I have to plug ln of 4x back in for u. So I have sine of ln of 4x, close it, plus c, and that ought to do it. Evaluate the integral of x squared over, in parentheses, 1 plus x cubed. All of it is squared. Well, when you see problems like this, you're thinking chain rule-y, quotient rule-y stuff. And when you do that, you use u substitution. So I'm always going to let u equal something that looks like its derivative is floating around. Okay, if I take the derivative of x cubed, it looks like x squared is floating around, so I'm going to have 1 plus x cubed be my u. You take the derivative of that, du dx, is going to equal 1 goes away, 3x squared. And then you do the old flip-flop with dx and 3x squared, giving you du over 3x squared equals dx. Now you take this guy, you take that guy, you take the original, you do some flippy-floppy, you do some substitution stuff. X squared is still lingering, but now we have u squared on the bottom because I replaced 1 plus x cubed with u, so u squared. And I'm going to replace dx with du over 3x squared, so du over 3x squared. So now we're integrating with respect to u. The problem is we have x squareds lingering. Not anymore. Let's rip out a 1/3, all right? So I have 1/3 integral of 1 over u squared du. Now, I don't like the way that looks, so let's rewrite that as 1/3 times the integral of u to the negative second power du. So when we integrate that, okay, we have 1/3 lingering. 1 plus negative 2 plus 1, u to the negative 2 plus 1. Since this is a indefinite, we're going to keep that arbitrary c kind of hanging out there. This becomes 1/3 times 1 over negative 1, so negative u to the negative 1 plus c. All right, so cleaning this up just a teensy bit. All right, we have negative 1/3. And let's drop that u downstairs and make it u to the positive 1 plus c. Am I done? No, sir, because u is not in the original problem. 1 plus x cubed is. So to finish this puppy up, we're going to call this 1 negative, oh boy, 1 over 3 times 1 plus x cubed plus c. And I think that should do it. Fun stuff. Evaluate the integral of e to the x over 4 minus e to the x. All right, well, when I see something like this, I'm thinking, all right, well, this is like quotient rule, and that's no good. So what I have to do is I'm going to let u equal the guy on the bottom. We're doing u substitution. Let u equal the guy on the bottom so that 4 will disappear. All right, so du dx is going to equal, go away, negative e to the x, right? Flip-flop the dx and the negative e to the x, so that will be du over negative e to the x equals dx. So now let's do some replacing. Integral of e to the x over u times du over negative e to the x. So now we're integrating with respect to u. Okay, you go away, let's bring a negative out front. So I have the integral of 1 over u du, which becomes integral of 1 over u is ln of u, so negative ln of u plus that arbitrary c, because this is indefinite. U originally was 4 minus e to the x, so to wrap this guy up, we are going to have negative ln of 4 minus e to the x plus c. And that's our guy, baby. Someone call the National Transportation Authority because this is going to be a train wreck. Let's let u equal everything underneath that cube root. U equals x cubed plus 3x squared plus 4. So du dx is going to be 3x squared plus 6x plus nothing. Do the old flip-flop where you're going to replace dx and that, guys. So du over 3x squared plus 6x is going to equal dx. All right? Now, let's take this fella up here, rewrite it out, and replace, well, first off, x squared plus 2x, nothing happens. Okay? That's going to be over the cube root of u. And then what I'm going to do is I'm going to write out, instead of dx, du over that. But while I'm at it, because I see some familiarity here, I'm going to rip out a 3. Okay, so I'm going to rip out a 3, leaving me with no way. X squared plus 2x. That allows these guys to cancel out. So let's do a couple things as we rewrite a bunch of stuff up here. Okay, we have the integral between 0 and 1. All right, why don't I pull out that 3 on the bottom, so that leaves me with 1/3 out in front. You're gone. Why don't I kill 2 birds with 1 stone? I'm going to move that upstairs. Make the exponent, so right now the exponent down there would be this. But if I move it upstairs, now it's going to look like this. Du. So now I'm going to integrate with respect to u. So 1/3 is still going to linger. All right, 1/3 is still going to linger out there. This is going to be 1 over 1 minus 1/3, which is 2/3, u to the 1 minus 1/3, which is 2/3. And I still have those limits of integration, but they have to do with x of 0 to 1. So I've got quite a ways to go before I'm super happy with what I have. All right, quite a ways to go. Let me, in fact, split this into 2 screens so I don't make this look worse than it's going to, because this is going to be a mess. All right, 1/3 is still out there. Okay, 1 over 2/3 is 3/2. That'll be nice because you guys cancel out. U, I'm going to plug that back in for u. Okay, so that's going to be x cubed plus 3x squared plus 4. And that's still going to be to the 2/3, right? With my limits of 1 and 0. So after cleaning all of that, I get 1/2. Okay, let's turn this back into the cube root of x cubed plus 3x squared plus 4. Actually, it's 1/2. Oh, boy. Oh, that would have been close. Squared. Limits 0 and 1. All right, so time to do some gross math. Plugging in my limits is going to be 1/2 cube root of 1 cubed plus 3 times 1 squared plus 4. All of that squared minus 1/2 times the cube root of 0 cubed plus 3 times 0 squared plus 4, and then close all of that. So you become 1/2 times the cube root. Let's see if we can do a little bit. 1 plus 3 plus 4 is 8, so the cube root of 64 minus 1/2 the cube root of, another mistake was almost made. 0, 0, and 4. 4 squared is a fun game, but it's also 16. So you become, the cube root of 64 is actually 4. 1/2 times 4 minus 1/2 times, I can't do anything, but I can pull out a 2, so the cube root of 2, I could do that. And this becomes 2 minus u cancel out the cube root of 2. So, not the prettiest problem on the planet. But yeah, that's how you would do it. Fun stuff. All right, when we see something like this, like the integral of 1 over a quadratic, we're thinking inverse trig stuff. And now it doesn't look like that, but this is how you approach a problem like this. I'm just going to pull this guy aside. And what I'm going to try to do is I'm going to try to make this look like 1 over x squared plus 1. I'm going to try to make it look like that, where it's not x. Maybe I should have used u. But I want to make it look something like that. So what I'm going to do is I'm going to pull x squared plus 4x and over here plus 5 to the side, and I'm going to complete the square. Now completing the square has you take half the number in front of x, which is 2, square that, which is 4, and then add that over here. Now if I'm on the same line over here, if I do something like that, if I add 4 to this expression, I have to subtract 4 to the same expression to balance things out. But when I do that, that allows me to turn this into x plus 2 squared, and this magically turns into plus 1. So now I can rewrite this integral as 1 over something squared plus 1 dx. And I could do u substitution and make it look like the inverse tangent stuff. So I'm going to let u equal x plus 2, which means du dx is going to equal 1, and du is going to equal dx. So now when I fill all this stuff in, when I put this all together, right, I'll have the integral of 1 over u squared plus 1 du. Okay? That becomes the inverse tangent of u, plus that arbitrary c, of course. And once I plug the fact that u is x plus 2 back into u, I have the inverse tangent of x plus 2 plus c. And that's going to be my guy. Okay, tricky stuff, very tricky stuff. Evaluate the integral of 1 over the square root of a quadratic. When I have the integral of 1 over the square root of a quadratic, I want to try to make it look like this. I want to make it look like the square root of a quadratic and see if I can pull this off. If I can do that, right, I can think inverse sine thoughts because the inverse sine comes from this. So this is what I need to do. Okay, let's get rid of that. I'm going to pull out just the stuff underneath the square root. Okay, so negative x squared minus 2x plus 8. Okay, and I'm going to think completing the square thoughts. Okay, so let's do this. Let's pull out a negative. So that leaves me with x squared plus 2x. Let's leave some space right here and keep that plus 8 out off to the side. Okay, now completing the square, this is going to be tricky, so kind of follow me here. I'm only inside the parentheses right now. If I were to take half of this, which is 1, square it, which is 1, and add 1 to that, I'm good. Now me adding 1 to this is the same as minus 1 in this whole chunk right here. If I were to subtract 1 from an expression, the only way to balance it out is if I add 1 over here. But this is good news, because what this gives me is negative. That becomes x plus 1 squared plus 9. Now rearranging it like that, right, because it's the same thing, and then turning u into 3, I now have what I showed you I needed from before. Okay, so I'm going to rewrite this guy up here as that, so I now have the integral of 1 over the square root of 3 squared minus x plus 1 squared dx. Using u substitution, I will let u equal x plus 1, so du dx is going to equal 1, and du is going to equal dx. So now I have the integral of 1 over 3 squared minus u squared du. Okay, that becomes the inverse sine of u over 3 plus that arbitrary c. Replacing u, I now end up with the inverse sine of, what was it, x plus 1 over 3 plus c. So definitely not an easy problem. Definitely not an easy problem. I got a little stumbled up here when I was trying to remember what I was supposed to do because inverse trig functions are not my favorite. But we end up with this, so yeah, not fun. Evaluate x squared, the integral of x squared over x squared plus 16. Now, usually when we see something that's all like quotient rule-y, we try to think u substitution. Well, that's not going to happen here. If you have the same degree up here that you have down here, you're going to approach this a little differently. I'm going to use polynomial long division. What I'm doing is I'm dividing x squared plus, 0x plus 16 divided by x squared plus 0x plus 0. X squared goes into x squared once. And so we write this down, x squared plus 0x plus 16. We subtract the entire row like that. You go away. Fortunately, you also go away, but you're left with negative 16. What does that mean? Well, this means we have 1 minus 16 over x squared plus 16. So now I can rewrite this problem like this. The integral of 1 minus 16 over x squared plus 16 dx. Split them up. The integral of 1 dx, I think I can handle that, minus, and let's rip out, I don't want to rip out the 16. I'm going to leave it there and you'll see why. The integral of 16 over x squared plus 16 dx. Now this guy is as friendly as they get, okay, x. All right, I'm not going to lose sleep over that. This reminds me of this. The integral of 4 squared over x squared plus 4 squared dx, which is giving me inverse tangent thoughts because that's exactly what it is. All right, x is still there, minus 4 times the inverse tangent of x over 4. Now I can't forget that since this was indefinite, that arbitrary c that's just kind of lingering. But that's what you get with a problem like this, okay? Inverse trig functions are tricky. This one forced us to do a little bit of polynomial long division, but we did it and we had fun. So here we are in section 14, which is basically approaching integrals in a different light. Now this isn't crazy, not at all. What I'm going to do here is I'm going to kill a couple birds with one stone and rewrite that cubed root of x as x to the 1/3. No big deal. But then I'm going to flip it upstairs and make it x to the negative 1/3. Still no big deal. Okay, taking the integral of that is going to have me saying 1 over 1 minus 1/3, x to the 1 minus 1/3. This is indefinite, so don't forget that plus c. 1 over 2/3, x to the 2/3 plus c. Let's multiply the top and the bottom by its reciprocal. 3 over 2, x to the 2/3 plus c. Now I'm going to rewrite this the way God intended. 3 square root of x cubed over 2 plus c. That's how I'm going to end this problem. Okay, you might have a teacher that might be okay with this. I prefer it to look like that. It just looks prettier. So we're going to go with that guy right there. This is section 14 of chapter 6, which allows us to do something and think outside the box a little bit. Now, it wouldn't be the end of the world to do u substitution, but we've done so many u substitutions that I'm going to approach this differently. I'm actually going to FOIL this guy out. Okay, this is a perfect square trinomial. So u become 25x squared minus 10x is minus 20x, and then plus 4 dx, and then I'm just going to integrate this the old-fashioned way. Okay, so you become 25 over 3x cubed minus 20 over 2x squared plus 40 or 4x plus arbitrary c, and cleaning this up a little bit is just going to get me 25 thirds x cubed minus 10x squared plus 4x plus c. Okay? So sometimes you can avoid use substitution. In a case like this, I did. Evaluate the integral of x squared plus 3, all of which is squared. Now, normally when we see stuff like this, we think u substitution, but u substitution won't work because you would let u equal x squared plus 3, and there's no 2x or anything with an x lingering around, so u substitution, again, will not work. So I am forced to FOIL this guy out. So I'm going to rewrite this as x to the fourth plus, what is that, 6x squared plus 9 dx. Now I integrate that using our typical power rule thoughts. So you would be 1/5 x to the fifth plus 6/3 x to the third plus 9x plus arbitrary c. And then cleaning this up in one more step, we have 1/5 x to the fifth plus 2x cubed plus 9x plus c, and that should do it. Fun. Evaluate the integral of sine x over cos squared x. Well, that is just disgusting and problem. I don't like it. Let's rip it apart. Okay, let's have sine x over cos x times 1 over cos x. Same thing, right? Well, I know that sine x over cos x is tangent x, and 1 over cos x is secant x. Now, we could look at this and be like, oh, I know what's going to happen, but maybe you would rather look at it like this. Secant x, tangent x. Same thing, just worded differently. The integral of secant x tangent x is secant x. And of course, since this is indefinite, arbitrary plus c, can't forget that guy. And now that problem, which looked like an absolute gross mess at first, wasn't so bad, was it? Evaluate 2x plus 1 over the root x. Now we're integrating this guy. I don't like it. So I'm going to rewrite it like this. I'm going to rewrite it like 2x plus 1. Okay, but I'm going to take the fact that I know that you're x to the 1/2 on the bottom, so moving it up top makes it x to the negative 1/2 up top, like so. I'm going to distribute that to both of these. So now I have, now keep in mind, invisible 1, and when you multiply two x's, you add the exponents, so this becomes 2x to the 1/2 plus x to the negative 1/2 dx. Now I can integrate, okay? So 2 just kind of lingers. You would be 1 plus 1 plus 1/2 x to the 1 plus 1/2, right? You would be 1 over 1 minus 1/2 x to the 1 minus 1/2 plus arbitrary c, of course, can't forget that. So the 1 on the left ends up being 2 times 1 over 3/2, I'll clean that up in a little bit, x to the 3/2 plus 1 over 1/2 x to the 1/2 plus c. U become 2 times 2/3 x to the 3/2, and u just become plus 2 x to the 1/2. Oh boy, I did not leave myself enough space. That's all right. We'll write small. Nothing magical happens here. 4/3, right? I will rewrite this as the square root of x cubed plus 2 root x. And maybe one more step is to rip out an x. 4/3 x root x plus 2 root x. I'm going to leave it like that. Not pretty. Definitely not pretty. I'm not happy with the way I ended it. But you know what? It's correct and it's good. And I forgot my plus c. That was a close one. I forgot my plus c. Oof. Definitely not my finest work. Let me quick rewrite it up here where I have all this Wonderful space, and I'll even use a thick pen. 4/3 x root x plus 2 root x plus c. Now everyone's happy, especially me. Ooh, I rhymed. Like and subscribe. Evaluate the integral of the 5th root of x over x. Let's change the way this looks. First off, let's change the fact that the 5th root of x is also x to the 1/5, right? So while I'm doing that, I'll make you x to the 1/5, and you're like, whoa, 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 what about the denominator? Let's move that up and make it x to the negative 1st. So times x to the negative 1st dx. Two x's are multiplied together, add the exponents, so this is x to the negative 4/5 dx. Integrating that is going to look like this. 1 over 1 minus 4/5, x to the 1 minus 4/5, plus some arbitrary c. So that's going to be 1 over 1/5, x to the 1/5, plus arbitrary c. Flip that upside down, you get 5. Turn that into the 5th root of x again, plus c. And that'll do it for the AB version of Chapter 6. I hope you had fun.